There is a drumbeat in the dark and you have never heard it. We imagine space as a place of absolute silence, a perfect, unending void where no sound can travel. We are taught that in space, nobody can hear you scream. This is mostly true, at least for our human ears. The vast emptiness between planets and stars lacks the medium, the air, that sound needs to journey from one point to another. Yet, the universe is not truly quiet. It is filled with forces and energies that create vibrations on a scale so grand, so monumental, that they are far beyond our limited senses. It sings a song, but its notes are played on an instrument the size of a galaxy cluster, and its rhythm is slower than the aging of mountains. This cosmic music is not something you can hear by simply floating in a spaceship and opening the airlock. It requires a different way of listening. We must use tools that can perceive the invisible energies that ripple through the cosmos and learn to translate the language of physics into a form our brains can comprehend. Before we can understand the sound, we must first understand the musician. What exactly is a black hole? The name itself conjures images of darkness and annihilation, a cosmic drain pulling everything into oblivion. That is not far from the truth, but the reality is more fascinating. A black hole is a region of space-time where gravity is so colossally strong that nothing, not even light, can escape its pull once it crosses a certain boundary. This point of no return is called the event horizon. These cosmic titans are born from the deaths of massive stars. When a star many times the mass of our sun runs out of fuel, it can no longer support its own weight. Its core collapses under its own immense gravity, squeezing an incredible amount of matter into an infinitesimally small point, called a singularity. But there is another class of black hole, the true giants of the cosmos. These are the supermassive black holes, which can be millions or even billions of times the mass of our sun. We believe these monsters reside at the center of nearly every large galaxy, including our own Milky Way. They are the gravitational anchors around which entire galaxies revolve. While nothing escapes from inside a black hole's event horizon, the region outside of it can be one of the brightest and most energetic places in the universe. As gas, dust, stars are drawn toward the black hole by its powerful gravity, they do not fall straight in. Instead, they spiral inward, forming a flat, spinning structure called an accretion disk. The friction and intense gravitational forces within this disk heat the material to millions of degrees, causing it to glow fiercely across the electromagnetic spectrum, especially in high-energy forms of light like X-rays. This is our window into their world. We study black holes not by seeing them, but by observing their dramatic effects on the matter around them. So, a black hole is not just a hole. It is an active, dynamic engine. It is a place of extreme physics where matter is torn apart, superheated, and sometimes violently ejected back into space in powerful jets. These interactions with the surrounding environment are what make a black hole more than just a passive sinkhole. They are cosmic architects, shaping their host galaxies through their gravitational influence and energetic output. It is this very output, this continuous pushing and pulling on the surrounding cosmos, that creates the conditions for the universe's deepest and most profound sound. The musician is ready, and its instrument is an entire cluster of galaxies. To appreciate the strangeness of sound in space, we must first remember how sound works here on Earth. Sound is simply a vibration, a pressure wave that travels through a medium, like air, water. When you clap your hands, you rapidly compress the air molecules between them. Those compressed molecules start a chain reaction, bumping into their neighbors, which then bump into their neighbors, and so on. This wave of compression and rarefaction travels through the air until it reaches your eardrum, which vibrates in response, and your brain interprets this signal as sound. The key ingredient here is the medium. This is why space is famously silent. The vast regions between stars and planets are a near-perfect vacuum. While not completely empty, the density of particles is incredibly low, maybe just a few atoms per cubic meter. This is far too sparse to carry a sound wave in the way we are used to. If you were to shout in the void of interstellar space, the vibrations from your vocal cords would have nothing to push against. There would be no medium to carry the wave, and therefore no sound would travel. However, the universe is not uniformly empty. There are places where matter congregates on a massive scale. The largest of these are galaxy clusters, gargantuan structures containing hundreds, even thousands of galaxies, all bound together by gravity. The space between these galaxies is not a vacuum. It is filled with a vast, diffuse cloud of gas called the intracluster medium. This gas is incredibly thin by earthly standards, much thinner than any vacuum we can create in a lab. But it is also incredibly hot, heated to millions of degrees by the gravitational forces of the cluster. And critically, because it is a medium, it can carry pressure waves. These pressure waves are, by the very definition of physics, sound waves. They are not the kind of sound our ears could ever detect, for two main reasons. First, the waves are incredibly low in frequency, meaning the peaks of the waves are separated by enormous distances and timescales. Second, the amplitude, or loudness, is spread out over such a vast area that its energy at any single point is minuscule. But these waves are real. They are ripples of pressure traveling through the intracluster medium, carrying energy from one place to another. Space is not silent after all. It just sings in a key that is far too low, and a voice that is far too grand for human ears to hear unaided. If we cannot hear these cosmic sounds directly, how do we know they exist? And how can we possibly listen to them? The answer lies in a process called data sonification. This is a powerful technique that scientists use to represent information as sound. Just as a graph can turn a list of numbers into a visual line that is easier to interpret, sonification can turn a stream of data into a series of audible tones. This lets our hearing, great at spotting patterns and changes, explore non-audible data collected as light, temperature, pressure. A simple example can help illustrate this. Imagine you are tracking the brightness of a variable star over time. You have a long list of brightness measurements. You could plot them on a graph to see flickering, or you could sonify them, assign a higher pitch to a brighter measurement, assign a lower pitch to a dimmer measurement. Play it back, and you hear the stars flicker as a changing musical note. A regularly brightening star makes a rhythmic melody. An erratic star sounds chaotic. Astronomers apply this to ripples in the gas of galaxy clusters. Using X-ray telescopes like NASA's Chandra, they create detailed maps of the hot intracluster medium. They don't see ripples directly, but measure subtle X-ray brightness variations. Those variations map to changes in density and to changes in pressure. Denser, higher pressure regions emit more X-rays and appear brighter. Less dense regions appear dimmer. Bright and dark arcs visually mark sound waves moving through the gas. Once pressure waves are identified and measured, sonification begins. Scientists take wave frequency data, how far apart they are and how long they take to repeat, and scale it up. They transpose the frequency by an enormous factor, like transposing music to a new key. They shift the ultra-low, inaudible cosmic frequency into human hearing. The resulting sound is a direct translation of a wave traveling for hundreds of millions of years. It is the voice of the cosmos, brought into our audible world. The first and most famous discovery of this cosmic sound came from a galaxy cluster known as the Perseus Cluster, located about 240 million light-years from Earth, one of the brightest X-ray sources in the sky. At its heart lies a giant galaxy, NGC 1275, which hosts a supermassive black hole. For years, astronomers using the Chandra X-ray Observatory studied the vast clouds of superheated gas that permeate this cluster. They noticed something strange, a series of vast concentric rings or ripples in the gas, spreading out from the central black hole like ripples from a stone tossed into a pond. These were not optical illusions. They were real, physical structures in the gas. The astronomers realized they were looking at the telltale signs of pressure waves, sound waves, that were being generated by the activity of the central black hole. As the black hole consumes matter and ejects powerful jets of energy, it periodically pushes vast amounts of energy into the surrounding intracluster medium. These outbursts create immense shock waves that travel outward, compressing the gas, heating the gas as they go. The ripples Chandra observed were the evidence of this process, a record of the black hole's rhythmic outbursts frozen in the X-ray light of the gas. When the scientists calculated the musical note corresponding to these ripples, the result was staggering. The note was a B-flat, approximately 57 octaves below middle C, a frequency more than 1,000,000 billion times lower than the limit of human hearing. To put that into perspective, a single oscillation of this sound wave, one complete vibration, takes about 10 million years to complete. This is, by an enormous margin, the deepest note ever detected from any object in the universe. To make this sound audible, the researchers had to raise its pitch by 57 octaves and 58 octaves. When they did this, they produced a deep, haunting hum. Not music in the traditional sense, but an eerie, resonant tone that represents a real physical phenomenon on an unimaginable scale. Hearing this sonification is like listening to the heartbeat of a cosmic giant. The discovery of the Perseus black hole's deep note was not a single aha moment, but the result of meticulous observation and analysis over many years. The key instrument in this discovery was NASA's Chandra X-ray Observatory, launched in 1999. Chandra is designed to detect X-ray emissions from extremely hot regions of the universe, such as exploding stars, galaxy clusters, the matter swirling around black holes. Its exquisite resolution allows it to see fine details that were previously invisible. When Chandra was pointed at the Perseus cluster, it provided an unprecedentedly clear view of the intracluster medium, the vast sea of gas between the galaxies. What it revealed was a complex tapestry of activity. At the center, the supermassive black hole in NGC 1275 was seen blowing enormous bubbles of high-energy particles into the surrounding gas. These bubbles are carved out by powerful jets blasting away from the black hole's poles. As these bubbles expand, they push the hot gas aside, creating a powerful shock wave that propagates outward. This process is not a single explosive event, but a continuous rhythmic cycle. The black hole seems to have periods of activity and relative quiet, sending out wave after wave, like a person rhythmically pushing water to create ripples. The faint, circular ripples that Chandra detected are the visible evidence of these propagating waves. By carefully analyzing the X-ray image, scientists measured the distance between the crests. They found the wavelength to be about 30,000 light-years. Using the speed of sound through the hot intracluster gas, they calculated the frequency. The result was mind-boggling, a note 57 octaves below human hearing. The sound was captured not with a microphone, but with a telescope that sees in X-rays. This is how modern astronomy uses different forms of light to reveal physical processes. X-rays tell us about pressure and temperature. Radio waves show the energetic jets. Visible light shows the galaxies. By combining these views, we can piece together the story. And if you're loving this cosmic mystery, tap subscribe, like, share, and comment. I hear the cosmos to join the journey. The sheer scale of this cosmic sound is difficult to wrap our minds around, and it comes with some truly astonishing facts. First, let's reconsider that frequency. A single cycle of the sound wave from the Perseus black hole takes roughly 10 million years. This means that during the entire course of recorded human history, from the first cave paintings to today, this cosmic sound wave has not even completed 1,000th of a single vibration. Dinosaurs roamed the Earth during one crest of this wave, and by the time the next crest arrived, they had long been extinct. It is a rhythm that operates on the timescale of planetary evolution, not the frantic pace of human life. This is the slowest beat in the known universe. Another surprising fact is the immense energy carried by these sound waves. While the sound is incredibly deep and faint at any given point, It is spread out over an enormous volume of space. When scientists calculated the total power of the sound being generated, they found it was equivalent to the energy output of 100 million supernovae exploding at once. This is a colossal amount of energy. The black hole is not just making a faint hum, it is pumping a universe-shattering amount of power into its surroundings through these acoustic waves. This energy travels through the intra-cluster medium, heating the gas and preventing it from cooling down. This leads to a fascinating and crucial consequence. This sound helps regulate the growth of the galaxy cluster. In theory, the hot gas in a galaxy cluster should gradually cool over billions of years. As it cools, it should condense and fall toward the center of the cluster, forming a torrent of new stars. However, observations show that far fewer stars are forming than expected. This is known as the cooling flow problem. The sound waves from the black hole provide a solution. The energy they carry reheats the gas, preventing it from cooling and collapsing. The black hole's deep note acts as a cosmic thermostat, keeping the galaxy cluster in equilibrium and stopping runaway star formation. And as if one record-breaking sound was not enough, astronomers have since found evidence of an even deeper note in another galaxy cluster, MS 0735.6+7421. Generated by one of the most powerful black hole eruptions ever seen, it carved vast cavities in the intracluster gas, estimated another octave lower than Perseus, suggesting acoustic feedback may be a common, fundamental process in the evolution of the universe's largest structures. The deepest sounds are not just a curiosity, they are a key part of the cosmic life cycle. At this point, you might be thinking this is all wonderfully strange, but does it really matter? Does a sound we cannot hear, from a black hole millions of light years away, have any real significance? The answer is a resounding yes. The discovery of these cosmic sound waves is not just a piece of trivia, it gives us a crucial piece of the cosmic puzzle. It helps answer the biggest questions about the life and death of galaxies. It shows the universe is a connected, self-regulating system. First, this discovery helps solve the cooling flow problem. Galaxy cluster gas should cool and form stars much faster than we see. The sound waves from supermassive black holes provide the missing heating. The black hole acts like a feedback engine. When too much gas cools and falls in, the black hole feeds and blasts out energy. Those sound waves carry energy that reheats the gas, slowing cooling. It's a self-regulating loop that keeps clusters in balance. Flowchart. Gas cools. Black hole feeds. Jets, bubbles form. Sound waves travel. Gas reheats. Second, this reveals a powerful new way black holes shape their environment. We once thought of them mainly as destructive sinks. Now we see them as cosmic engineers. Their outbursts and sound waves can influence hundreds of thousands of light years. They can control star formation across entire clusters. That changes galaxy evolution models. Central black holes are pivotal. Finally, it deepens our sense of wonder and connection. Our senses are limited. Light we cannot see, forces we cannot feel, sounds we cannot hear. By building X-ray telescopes and using data sonification, we extend our senses into the cosmos. Hearing the deep hum of a black hole is a genuine glimpse into the universe's hidden machinery. A voice that has been singing long before we evolved an ear. If this changed how you think about silence in space, hit subscribe, like, and share to help more people hear the universe. Drop a comment. Deepest B flat if you made it this far. We read everyone. As we draw this cosmic journey to a close, let's step back and consider the grand picture. The universe is not a silent, static collection of objects. It is a dynamic, evolving symphony of interacting forces. The deep note from the Perseus black hole is just one instrument in this vast orchestra. Other black holes, stars, cosmic events are playing their own parts. Some might be like the screech of a violin, representing fast, violent events like supernovae. Others might be a steady, rhythmic drumming, like the regular pulses from a spinning neutron star. The universe is alive with these unheard vibrations. The method of data sonification is our concert ticket, a way to translate the score of physics and light into sound. Every time we point a telescope at a new object and translate its data into sound, we are listening to a new part of the cosmic symphony. We are learning about the tempo, the rhythm, and the harmony of the universe's evolution. These are not arbitrary sounds. They are the audible expression of real physical processes: rotation of a planet, the flickering of a star, rumbling of a black hole. This exploration reminds us that reality is far more complex and beautiful than what our immediate senses reveal. The world is full of hidden music. Bats navigate with ultrasonic chirps we cannot hear. Whales communicate across oceans with low-frequency songs that travel for hundreds of miles. The ground beneath our feet is constantly vibrating with seismic waves from distant earthquakes. The universe is no different, just on a scale that is almost beyond comprehension. The deepest sound from a black hole is a powerful testament to this hidden reality, a physical process that shapes galaxies, yet remains utterly imperceptible to us without the aid of science. So, the next time you look up at the night sky, remember that it is not silent. It is filled with the deepest bass note imaginable, a hum that has been resonating for eons. It is the sound of a black hole keeping its galactic house in order. It is a reminder that there are still so many secrets waiting to be uncovered, so many more instruments in the cosmic orchestra waiting to be heard. What other sounds is the universe making? What other fundamental forces are shaping the cosmos in ways we have yet to discover? The universe is not silent. We are just learning how to listen. If this moved you, subscribe for more hidden sounds of the cosmos. Like, share, and comment your favorite cosmic instrument.